right, so yeah, cars. So first let's start with a little bit about me. I've actually had a variety of different things I've worked on. I actually got started running ISPs in high school. Yes, people trusted me with T1s and lots of modems. And I spent a bunch of years writing performance analysis tools, so things like statistical samplers and hooking in and making processors do things that you probably didn't know they can do. And then most of my career has actually been working at Google, working on server health monitoring, trying to predict failure of components ahead of time and automate those things. I've also done a whole bunch of other side projects that have led into various hobby things, but satellite flight computers, navigation systems, precision antenna aiming, and theft prevention, which is always fun. We can talk about how to cheat theft prevention systems later. Vehicles for me are really just a hobby. I don't have any particular interest in commercial parts of it. This is actually what I ended up tuning. It's sitting in my garage currently. So a coworker said, hey, does anybody want to work on a drag race car? And I said, sure, I'd love to figure out how to tune an engine. So this is a 96 Ford Cobra. It comes with a 4.6 liter V8. This has been completely rebuilt. It should make a little over 1,000 horsepower with nitrous. And I've basically gone through and redone all of the wiring, verified all the sensors work, fixed up the fuel systems, et cetera. And I'm now getting to the point of actually going through and tuning the engine behavior and working on getting it ready to take it to a dyno to see what we actually get power-wise. Interestingly, we ran this last year a couple times at Sonoma just to see what would happen. And we were running like 11-second quarter miles. And then I found out that 2 of the fuel injectors were stuck closed, so we only were running on 6 cylinders. So a little bit about engines. How many people know the basic operation of a 4-stroke engine? Yeah, okay. So it's essentially this piston is going to move inside the cylinder, and it's going to do that twice for every complete cycle of the engine, which gives you 4 strokes. And so you have these valves at the top, and basically you go through an intake stroke where you're pulling air and fuel into the cylinder through the intake manifold. Then both valves close and it compresses it. When it hits the top, the spark plug fires. The explosion pushes the piston down. That's your power stroke. And then the exhaust valve opens, and as it comes back up, it pushes all the exhaust gases out, and then it repeats. And this is just happening on all the different cylinders. We have 4 cylinders, 6 cylinders, whatever. There's a whole bunch of different components because you're actually trying to contain explosions. I mean, they're calling it combustion. It's a controlled explosion. But the main thing in a 4-stroke engine is the crankshaft is going to turn twice for every single turn of the camshaft. And this comes into play a little bit later. And what you're really trying to do is combust a fuel-air mixture at the optimal time. Because if you hit it just right, the fuel will burn, and when it gets to the point where it's actually expanding as it combusts, that will be at the point where this piston is sitting at the top of the stroke, and you'll get the most energy out of it as it pushes the piston down. So the 3 things you need in general for cars to work, they always talk about the 3 ingredients for combustion: air, fuel, spark. If you ever have a problem with a car and the engine won't run, it's one of those 3 things, guaranteed. So a key part of that is the air-fuel mixture ratio, often called AFR. And what this is a ratio of the mass of air to the mass of fuel in the air-fuel mixture. It's important to say mass, not volume, because as the engine warms up, things change. So by going by mass, you actually get a more accurate representation that's consistent across different variables. The stoichiometric for gasoline is approximately 14.7 to 1. So that means if I have 14.7 parts air to 1 part fuel, and I combust that, it should result in only combustion byproducts. There should be no fuel and no air left. Peak power output and overall best performance is actually slightly lean of that, which means slightly more air. But there's a variety of reasons why you don't necessarily want to run there. In general, as you move with more fuel, so you make it rich, you end up with a cooler combustion, so the engine runs cooler. And as you run lean, you get more power, but it gets hotter. Yes?
Is it oxygen or is that sea level?
So it's air, and we'll get to other parts of it. It's not necessarily at sea level.
Maybe I'll ask you later. This should be a diagram.
Yeah. So a couple things to think about in an engine is when you push the throttle, you're actually not controlling the fuel. It's not actually a gas pedal, it's an air pedal. What you're controlling is a throttle plate that's in the intake, and then a ECU is, or a carburetor or a mechanical fuel injection system, whatever it's doing, is actually adding correct fuel amount to match the amount of air you drew in. So it's always pumping air through, and you're actually trying to measure the amount of air that you pulled in so that you can add the right amount of fuel. This was originally done with mechanically controlled through carburetors and distributors and things like that, and slowly as the emissions controls laws went into effect and you had to do better on those things, they moved to electronic ignition systems and EFI systems, and so now we end up with where we are today, where everything is computer controlled. Okay, slight note on terminology. We talk about ECUs. Historically, that meant an engine control unit, but as cars have gotten more advanced, that's become a generic term for electronics control unit. It basically covers anything that's sort of a separate module inside the car. Most of the time, what we're really talking about is called a PCM in the industry, a powertrain control module. And those are, terminology varies from vendor to vendor. Essentially, powertrain can include the transmission. Oftentimes it does, sometimes it doesn't. But there are other units like your power steering control, your braking control system, etc. And these are all separate systems usually in cars. Okay, so we need to measure air. So how do we do that? Well, one way to do that is a throttle position sensor. This is kind of the classical way. Basically, you just put a potentiometer or an encoder on the actual throttle mechanism. And so you're just, you record the set points on the potentiometer at the extreme open and extreme closed. And then you can infer, you can measure it and interpolate where you are. This doesn't actually directly measure anything. You don't actually know what's coming through to the point about temperature. As air temperature changes, the mass of air is going to change. As pressure outside changes, that's going to change things. But you can still get pretty close. And this works okay when you have a naturally aspirated engine. What that means is the intake runs through a hose. The intake manifold has a set of tubing that runs out through like your air cleaner and basically goes straight to the atmosphere. So it's just sitting at whatever the atmospheric pressure is. But when you have a forced induction system like a supercharger or a turbocharger, where you're actually putting a compressor in front that's compressing the air before it goes up to the throttle plate, this gets really, really tricky because it's even harder to think about what's actually happening at this given throttle position. Sometimes this is used in combination with other systems where you actually are measuring the air mass, because this does actually tell you what the pedal behavior is. And that tells you what the user intends, right? The driver, if they mash the pedal, you know that they're trying to accelerate really hard, and you might use that to compensate and add additional fuel to quickly speed up. Okay, so how do we do better? Well, the most common way that you've, until past 5 or 6 years ago, was manifold air pressure. Essentially, they take an absolute pressure sensor and attach that to the intake manifold after the throttle plate. Now, think of the engine is running, it's a pump. It's trying to pull air. So it's actually sucking air past the throttle plate. So inside the intake manifold after the throttle, it's usually running at a vacuum. And so that's why you use an absolute sensor, is that you actually can see below atmospheric, you can measure the vacuum. So that's the normal case. For example, in that Cobra at idle, it's pulling a vacuum. It's down at about 50 kPa, so about half atmospheric inside there. When you have forced induction, you're actually compressing the air going in, and so depending on the circumstances, that can cause the manifold pressure to actually be above atmospheric. So you can actually run well over 100 kPa. Often you buy a 3-bar or 300 kPa map sensor. And that way you can actually measure all the way out to extremely high boost that you'd use in like a drag race car or super high output. When you combine the map with air temperature sensor, the measurement of the nominal cylinder displacement, so the actual volume of the cylinder, and volumetric efficiency, you can roughly guess what the air mass is, because you're essentially calculating the volume of the cylinder, and then you can calculate the density of the air and work it out. This works pretty well. There's some odd effects because you're still measuring the air indirectly. But this was pretty much the standard quo for a long time. The newest technology out there is mass airflow sensors. What these actually do is they put a heated wire inside a fixed size plenum. And this is inside the intake tubing. And it's usually before the throttle plate. So it's actually, yeah, it's before the throttle plate. So it's earlier in the intake system. So it's closer to where the air is actually entering the car. Now, the way this works is the wire is heated to a temperature, and they measure that. And then basically, the air coming through the plenum, as the airflow increases, it cools that wire more and more and more. And so they look at the temperature differential across that, and that tells you what the actual airflow is. And because you know the air temperature, and you know the flow rate, and you know the size or the diameter of the plenum it's passing through, you can calculate actually what the intake amount of mass of air. So this is pretty common on the newest cars that you're buying. So I mentioned volumetric efficiency. Engines are imperfect. When you actually look at all of the pieces I've described so far, like the intake tubing, the valves, the throttle, these all restrict air from coming in. So it's not acting in nominal behavior. When the cylinder goes to pull, it's creating a vacuum because it's fighting to pull the air through. The valves and rings inside the cylinder leak. So air will go down past the piston. It'll go through gaskets. It'll go all sorts of places. And you also can have just sort of things that are natural in the operation. They're actually intentional design choices. Like you can have periods where the intake and exhaust valves are both open. They do this in extremely high power engines. It gives you a lot better power at the high RPMs, but it actually means the engine can barely run at an idle. If you ever are like at a drag strip and you hear an engine that's kind of going blah, 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 that's called loping, and that's what that actually is cam overlap. So these imperfections are expressed as a percent of the perfect or nominal condition, and this actually is expressed in VE, where it's a ratio of the actual air mass that ended up in the cylinder versus, or over, the nominal air mass if you assumed 100 kPa and you assume some known temperature. Usually, a lot of the calculations people just say, it's 20 C, 100 kPa. You just assume that's what your nominal condition is. Now, because you can have boost in forced induction systems, this can actually go above 100%. It's not uncommon to see 200 to 300% VE when you're at certain sections of forced induction. So putting this information together, I now have a model of I'm measuring the air and I know the actual mass of that. Well, how do I figure out what fuel I want? Well, ultimately what you're going to fill in is a fuel map. And usually these are expressed as these 3D views where you're basically saying you have one axis that is some indicator of how you're measuring the airflow or the air mass. So if you're using throttle position, they often call it alpha N. Alpha is the throttle position, N is the engine speed in RPM. Or if you're using MAP or MAF, you're using a speed density model, and then basically that axis changes. Instead of being 0 to 100 on the throttle position, it's now actual manifold pressure in kPa, or it'll be the actual air mass if it's a MAF sensor. Both of them use engine RPM on the other axis because it changes over the entire range of it. This is actually where I'm currently at with tuning the Cobra. This whole area is basically unexplored. I haven't even gotten there. But you can see there's already these little peaks and valleys inside around idle and low speeds. It's actually hard to go less than 30 miles an hour without going, 1,000 RPM. So anyway, you're trying to construct this and you do it experimentally. Yes, we can nominally look at what the air mass is and say, oh, I want to hit stoichiometric, but because we don't know what all those losses are and everything else, we don't actually know what VE is. Okay, so what do we do with this map? Like, what does it actually, how do we translate that into fuel? Well, fuel injectors are pretty simple. They're solenoids. They do come in two variants of low impedance and high impedance. The idea is whether or not you want it to slam open really fast and then have less hold time, or whether you want it to be a more sustained open. It's a debate as to how much that really matters. But essentially, you have pressurized fuel off your fuel rail. Your fuel pump runs it. What the actual pressure would be depends on application. 40 psi is not uncommon, 80 psi for top fuel type applications. And essentially, when the solenoid triggers, it pulls the plunger up and it sprays it out through a spray nozzle. You get atomized fuel. There's a lot of voodoo in these about optimal spray patterns and all sorts of stuff as to what you do. But mostly what you're thinking about in this is they're rated by the sustained flow rate in cc per minute. You'll often see them marketed in pounds per hour, which is really just looking at the nominal fuel. If you look at like a 14.6, or you have to look at the specific gravity of fuel and all these things. But if you just look at cc per minute, you kind of get a good feel for where they're going. And that's important because when you get to the really high ends, you can actually run out of fuel injector flow rate before you actually run out of power capability in the engine. And the way the ECU runs these is it PWMs them. It's pretty straightforward. As long as you can build a 4 amp capable PWM output, then you can drive fuel injectors. Okay, but we need to experimentally determine what fuel values to put in, and really that comes from the VE. So the way we do that is with oxygen sensors. Now, an oxygen sensor measures oxygen, right? Kind of. It actually measures a ratio of the oxygen in the exhaust output, in the exhaust tubing, usually in the downpipe, right, as close to the engine as you can get, practically. And it's comparing that to the oxygen content in free air. And what's really happening is there's a complicated sensor in there, or actually a really clever sensor, that as the oxygen ions get passed over the sensing element, it induces a voltage. So on a simple oxygen sensor, it's 2 wires, and you literally just read the voltage off of it, and it tells you what your fuel rate, how much oxygen is left. And because you know what stoichiometric's supposed to be, you can see, oh, it should be exactly this if I had practically no air left in the combustion at the end. Now they come in narrowband and wideband variants. So let's talk a little bit of a detour. You might have seen that I call it a lambda sensor up top. Why do I call it lambda? Fuels have different energy content and they have different actual fuel ratios that you use. So mostly I've been talking about gasoline. That's what we're used to. It's around 14.7, but even with that, if you buy 116 octane fuel, then it has more of like a 14.3. And you also run into things like, for certain applications, you might run E85, so ethanol, or M85, which is methanol. And when you get into those, it's totally different. Even propane, LP, there's all sorts of different fuels. People run cars on all sorts of things. Lambda is a way of normalizing that, to think about it in terms of how far away from stoichiometric are you. So essentially, it's taking the AFR that you're currently at and expressing that as a ratio over the stoichiometric AFR. And so you end up with 1.0 lambda is I'm stoichiometric, and less than 1.0 is too much air, you're lean, and over 1.0 is, less than 1.0 is rich, you have too much fuel, and over 1.0 is lean. Okay, so a narrowband oxygen sensor. These are really what early ECUs use. These are actually really common. This is when you see that your oxygen sensor has failed in your car and you wonder why it's limping along. Basically, it is that sensor. It really only measures this very narrow range between 0.9 lambda and 1.1 lambda. Sometimes it goes out to 0.8 and 1.2. But the thing is, it has this S-shaped response curve. So it really only tells you, am I rich or am I lean? It can't tell you by how much because the response is just not there. Now, this is what most computers in cars ship with, right? This is if I go buy my car and it runs normal operation, that's all it cares about because it's trying to adjust its loop, and it doesn't really need to know exactly how far off it is. It just kind of tracks over time. But when you're actually doing tuning or any sort of engine performance analysis, you want a wideband oxygen sensor, which it actually is the same sensing element, but they do some additional circuitry around in putting an electrochemical pump in there that helps with actually expanding the sensor reading range, and you end up with a more linear relationship on the output. And so now you can measure from 0.65 lambda all the way up to infinity. These are really complicated to operate, though, and so they're actually dedicated interface ICs. There's a link to the data sheet for one from Bosch. But essentially, like, you can buy a little chip that has a SPI interface, and it will take care of actually doing all the driving for the elements. Now, one thing to know about these, they all have heaters. If you turn the heater on before you actually heat up the exhaust, you will kill the oxygen sensors. So your car knows how to do this normally, but if you're buying aftermarket parts, it's really common that people will, hey, I warmed up my oxygen sensor and it died all the time. Stop doing that. Okay, so now we have a way to measure the oxygen, and you can relate that back to what your air-fuel ratio is. Now we have to choose what we want those to be. Because I can actually run the engine over a wide variety of AFRs. It will operate. But what I'm trying to do is optimize for different types of driving conditions and whether I want the engine to have maximum power output, be super efficient, whether I need to actually have more fuel to keep the engine cool. So this is a pretty typical layout, and this is where everybody would go. You know, at 0 PSI and 0 RPM, the engine is not running. And so you'll have the starting condition, which is usually pretty rich. And then you'll go into these ranges where, like, idle is anywhere from 13 to 15, which is sort of slightly rich, slightly lean. You just sort of give the engine whatever it wants because it's not under any load. Down here where it has vacuum, this is usually the range where you're actually either idling or cruising. You know, you're not actually putting the engine under a huge amount of load. It's not doing a lot of work. And usually you actually run that slightly lean because that gets you the best fuel efficiency. You just don't need a lot of power. It can run hot because it's not actually doing a whole lot. As you move up and you're actually putting the engine under more and more load, now think about, we're measuring, in this case, this is looking at the manifold pressure, and it's doing it as a booster vacuum. But as you increase the throttle, you know, if you're climbing a hill, you have to push the pedal more. You're actually letting more air in, and that's going to increase, and you're going to see actual either less vacuum or all the way into boost, depending on your forced induction or not. And as it's doing that, you're going to actually be cramming more air-fuel mixture into the same volume inside the cylinder, and so the explosions get bigger. And so as you do that, you want to actually keep adding more and more fuel because you actually need the fuel as a cooling agent. This becomes even more important when you run things like methanol because methanol actually carries its own oxygen with it, so the energy density is lower, but you actually get more output out of it because you don't have to bring as much air in. And you easily can melt components by running the engine too hot. There's lots of interesting things about methanol. Okay, so that's about the air-fuel mixture and basically metering that out. Once you have all that, the next part is the ignition, right? So I have my fuel map. It's getting fuel into the cylinder at the right time. Now I need to fire the spark plug at the right time. Well, it takes time for all that fuel and air to actually combust. So I have to time the ignition so that it happens, so that at the point where the cylinder or the piston has reached the apex of its stroke, that is when it actually starts expanding and exerting the most force back on the piston. So I get the maximum power output. Now, exactly what that duration is completely depends upon how much fuel where are you at in your operating mode, and is it how much air-fuel mixture is actually inside of the cylinder at that time. There's tons of factors that will change that. So you end up with a similar map. You have the ignition map because you've got to plot this out the same way. Now the main thing when you're running the engine control unit is ignition systems are really simple. Basically, you just have a gigantic step-up coil and you pulse 12 volts on it. It's literally just a FET hitting 12 volts on the primary side. and the secondary runs, and these are the firing aspect here is usually aftermarket runs 35,000 volts, 40,000 volts. But yeah, they're fun to play with. So when we're thinking about the timing, we need to think about the overall stroke and operation of the engine. So you'll hear people talk about top dead center. And what that really means is the position on the crankshaft, because the crankshaft has connections to all the pistons. So these are all mechanically related. Where the piston is at the top of the cylinder. It's at the apex of its stroke. Usually we only talk about this on cylinder 1. Because all of the cylinders are connected, everything's connected, you just need to deal with one cylinder and you may as well pick number 1. Now remember, that happens twice per crankshaft cycle. Or you will have this happen twice per engine cycle, right? So the timing is often described as degrees before top dead center. Just because you're thinking about it, the crankshaft is going to be in this position, and I need to ignite, and then it has to travel that many degrees before it actually hits the top of the compression stroke. Okay, so how do we know that? Well, you need some sort of position sensor. So crank position sensors are 2 parts. One part, well, first of all, the crank position sensor is usually called a ref signal. This is sort of the basis of all of your timing inside of an ECU. You have to know how fast the engine is going. And so you mount a trigger wheel onto the crankshaft, and these have various teeth configurations. A very common pattern is 36 teeth, 1 missing. There are also cases where you have additional teeth. You might have multiple missing teeth. It just depends on what your application is. Then you put a Hall effect sensor or reluctance sensor up aligned with those teeth so that you can actually get pulses that with each tooth, and you'll actually see where you're missing the pulse, and you know that that's the exact position of where the missing tooth is. Pretty simple system. Cause lots of trouble because people miscalibrate the sensors all the time. And when you do this, you might naively think, oh, well, I have this missing tooth. That's my index position. I want to set that right at top dead center. Why is that a bad idea? I know it's on the slide, but... Well, if you do that, you have to respond to that signal instantaneously because that is the top of the stroke. And I actually want to fire before that. And I actually have to think about that signal a little bit to decide exactly what I'm going to do. So I actually want to set that at some arbitrary position on the crankshaft and then tell the ECU, by the way, when you get this pulse, you're at 400 degrees before top dead center. And then the ECU will count down until it hits the right points. Now you have the exact same setup, but on the camshaft. I haven't talked about the camshaft very much, but the intake and exhaust valves are controlled by a separate shaft. That's the camshaft. And it's literally a lobe shaft that just pushes those down, fighting springs. Now the camshaft only rotates once per engine cycle. So for every 1 turn of the camshaft, you get 2 turns of the crankshaft. So the trigger wheel on a camshaft, same exact thing, except that the index here tells you not only top dead center, but top dead center of the intake stroke. So they call this the sync signal. It's basically, I know where the start of the overall process is. And again, you want to set this in a position that is offset from both top dead center and the crank position because you don't want to have the ECU trying to respond to 2 pulses at the exact same time. Okay, so basic open loop operation then is the ECU waits for the sync pulse. Just think of it as an arm. And that tells me I'm coming up on my top dead center of the intake stroke. I wait for the sync pulse or the ref pulse, which tells me I'm actually coming into the actual top dead center is coming, right? And I already know it's for the intake stroke. Now I know that it's actually coming. Wait until I'm actually, well, I did that wrong actually. I was writing these at the last minute. So you would start spraying fuel before top dead center. You would actually, well, I did that right. You want to wait till top dead center because I know that that's coming before at the beginning of the intake stroke, and I want it to actually spray fuel in and have it be pulled into the cylinder as the intake stroke's happening. Then I continue timing until I actually hit the exact ignition time that I want, which is slightly before this gets up all the way to the top. We ignite, and ultimately this is going to rise up to the top, and hopefully the force pushes it all back down. And when you do this, you also then go back and record your measurements from your MAF and your MAP and air temperature sensors and everything else, and basically update your estimate of what the air mass would be, so that the next time you know what section of the fuel map to go to. In a closed loop operation, you basically assign, hey, the ECU, you're allowed to go ahead and go, say, 10% on your fuel amounts. And you can do that based on looking at the oxygen sensor output. And so it will dynamically see, oh, I'm running lean for some reason. We don't have no idea why, but it has liberty to apply some amount to get you back to what your target lambda is. Okay, we've talked about a lot of sensors. We talked about a lot of basic operation. Knock and ping. How many people have heard of knocking and pinging in engines? Okay, everybody probably knows that those are really, really bad things. So knock in an engine is basically some sort of mechanical hit inside the engine. And that's where the knock sound comes from. There's lots of different causes for knock. Sometimes it's because the actual bottom connecting rod between your piston and the crankshaft has come off, and so now it's literally thumping away. Ping is usually more referring to a softer noise that sounds more like somebody's sitting there with a little hammer inside the camshaft going ting, 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 ting. And it runs with the engine RPM. Now, what happens in pinging is, there's a couple different causes, but a most common one is that the air fuel is detonating instead of combusting. And what they usually mean by that is, when you combust, you start the ignition with the spark plug, and it burns completely around from that point and sort of has a single flame front moving through, consuming all the fuel. When it detonates, you'll actually have different pockets all going at different times, and so it will burn either much faster. It'll burn much faster with much more energetic. You can cause this by having too advanced of timing, so you're actually triggering the ignition too early, and it's not as compressed as it should be. You can have this if you run really lean. There's lots of different reasons, but when it happens, you can see up here, basically, the explosion starts before the piston's actually all the way at the top. It starts fighting the piston as the piston's trying to travel up because the crankshaft is pushing it through the inertia of the drivetrain. And the piston will actually slap into the side of the bore of the cylinder, and that's where your pinging sound comes from, because there's a little bit of tolerance in there. This is extremely destructive to engines. This is just one example I pulled. This is actually, I'm part of a Facebook group that is all about EFI engine tuning, and it's literally destruction photos like this all the time of people's engines, and it's stuff like, how did you put a hole in the block of your engine? Okay, so knocking is really bad, so what do we do about it? Well, a lot of modern cars have knock sensors. These are basically microphones that are bolted to the engine block. In fact, it's really common for people to buy these, actually hook them up to a standard microphone input on your laptop, and then run standard audio analysis programs on them. The trick to all of this is an engine is a noisy thing to begin with. So you're actually having to figure out what is a knock, what isn't a knock. There are lots of complicated boxes for these things. You know, there's all these sort of headphone setups and everything when you're trying to figure out knock on your own. And this is actually pulled from one of those systems that you see sort of this overall normal noise floor, but then when you have a knock, it's pretty energetic. You see it. And what you're trying to do is isolate that and notice that it happens. When you do that, you actually want to probably retard your timing. That's most likely what the cause is. You might, if you know that you're running lean, add some fuel. You could also be running way too hot. There's a variety of other things that could be happening. And so that's the basic sensors, although there's a ton more. I've mentioned things like air temperature. You also want to monitor coolant temperature, because if the engine gets too hot, that's a problem. Oil pressure, boost control. You can actually vent off excess boost if you want to have more control over what the overall engine behavior is. Idle control, where it's dynamically controlling the throttle at idle. Vehicle speed sensors, gear indicators, nitrous switches, the list goes on and on and on and on and on. But that was kind of the summary of the different sensors that are a little bit key to the operation. That's all I've got. Any questions? Yes?
Before they had like the oxygen sensor, did they just sort of guess that stuff, or what did they do?
So as you notice, like in a normal car, if you run open loop, you don't actually need an oxygen sensor, right? The manufacturer would use, say, a wideband oxygen sensor at the factory when they're designing the car to come up with the actual fuel map is. But every engine should be within a reasonable tolerance of that. So they just load that map in, run it in open loop, and call it good. You can't compensate for all conditions, so that's why they started introducing oxygen sensors as a normal feature of the car. Is then it allows it to run closed loop and hit slightly better on emissions.
Was it required essentially for the catalyst to work, right?
So they are somewhat related to catalytic converters. If you run way too rich, you can actually destroy catalytic converters. If your exhaust gas temperatures get too hot, you can destroy catalytic converters. They're fragile things, expensive fragile things. So yeah, a lot of these things come in because in order to solve one emissions problem, you create another problem, and you have to add more sensors and more control over it. Yes?
In practice, how did you program those? Like, did you build your own drivetrain control module, or did you take commercial ones and reprogram them?
So I thought about putting stuff in here, and it turns into a giant rat hole. This is a space that really needs software engineering help. Essentially, like, people take the stock OEM ECUs and run hex editors on the firmware. They go and find the locations and figure it out. Or they'll hook into the CAN bus and find out the protocol messages to update things. There's a variety of systems that actually hook in parallel to the ECU and lie to it to get the behavior you want. In the case of the race car, it's a completely aftermarket system. I don't have any of Ford's original equipment in there. And in that case, you just get a full software program that lets you configure all this stuff much more easily. It's not a well-established area. I mean, it is in terms of if you want to go buy something and build a car and do tuning, all that's available to you. It's really expensive. If you're looking to hack and explore, there are people who build their own gadgets and sensors and little adapters, but there's not so many people building full ECU type units or PCMs. There's a couple out there, but they're kind of complicated things and people just haven't invested the time into it. Yes?
Hi. Thank you. Given that I've had the knock part in my driving career. Not good. What about a hydro between diesel and...
So diesel's quite different. Gasoline, methanol, ethanol, propane, they're all combusted, they all use spark plugs. In a diesel, you're actually trying to do more of what causes pinging. You're trying to run the fuel at a hot enough point and run to enough compression that it actually detonates on its own. That's how a diesel engine operates, and that's why they can run on things like cooking oil. They run much higher compression ratios, and so it's a slightly different system in that you're not actually trying to control the ignition timing at all. You're really just trying to control the fuel map. Yeah?
What are the limitations in terms of advancing the cam timing and things like that? Do you have to go to, are the newer engines completely electrically actuated, or are there ways to manipulate the timing between the crank and the cam?
So crank and cam are almost always directly connected. When you go in and have your timing belt changed, that is what they are changing, is the belt that locks those two together, because you want them to be synchronized. There are things like various technologies for doing variable valve timing, but it's usually still you have a the crankshaft for driving the pistons and you have the camshaft for driving the valves, And it's minor mechanical adjustments to basically get the valves to fire at slightly different times. There's been a couple attempts at doing things like electrically controlled valves, but it's never gotten to the point where it's quite feasible. If you look at the progression of fuel injection, it actually started with carburetors, then they went to central fuel injection where you had, because the injectors couldn't withstand the pressures and heat of being close to the engine, they basically just put it where the carburetor was, further up in the intake. As the injectors, materials science came better, the injectors became more rugged, they moved it to port injection, which is where it's sort of right near the intake valve. And nowadays you actually have direct injection where it's actually directly in the cylinder. The intake valve is only to let air in. So similar things are likely to happen for the actual valve control, but more or less you're running the valves and the crank in synchronous. You want those to be synchronized.
So what happens when you add nitrous to the mix? Can you give us a rough overview of how that changes the mix?
So today I have got the nitrous all turned off because it adds a lot of complexity. The way to think of nitrous is you're adding an extremely potent fuel to the mix. And there's a couple of things you have to consider. One, you don't want to do that all the time. So that's why in every car movie you see them hit a button and it fires it, right? You actually want to have a whole system. You want it to have to arm the thing. There's lots of safety measures you want there. One of those things is actually flipping a signal to tell the computer you're actually going to do nitrous, because you actually want to change your ignition timing because you know it's going to run hot really quick. So you want to richen things up, you want to adjust it on your timing for sure. You probably want to adjust your fuel. And then you usually have an entirely separate setup for metering out how much nitrous you're actually going to inject. Most people run wet nitrous systems where they actually have a separate fuel rail that comes up to a separate solenoid for fuel control and nitrous control that then merge into on the intake manifold, because you don't want to actually just run dry nitrous into the main intake. You can actually have explosions inside the intake manifold by accident. Pretty common actually. When you see when you see drag race cars, engines explode, that is one of the reasons that happens. Yeah.
So you're talking about preventing things running too hot.
Mm-hmm.
I mean, isn't there better ways to just create better cooling so that we actually can run it hot? Because it sounds like running hot means I can get the most optimum power effects. So
Yeah, it's true. As you run hotter, you're getting usually better performance. The challenge is it's really about the strength of the engine block. So your coolant, if we go back to one of the early slides, like here, you can see there's actually slots that border around the actual cylinder, and that's where your coolant actually flows. And that's plumbed all the way through for your water pump and everything. And that reduces the thickness of the wall. So you actually have this trade-off of, as I add material to strengthen the wall of the cylinder so that it can withstand more explosive force, I actually create more thermal mass that it's absorbing into. So now what do I do about the cooling situation?
well, I mean, we've learned in other contexts, like computers, for instance, heat pipes can create from a relatively small area can pass away a lot of heat, and then we can just secondary cool that. I mean, are there things like that?
So usually when you think of heat pipes in computers, you're relocating heat, and you have to consider what the capacity of that is.
Yeah, sure. But
Think of it this way: your engine is already a liquid-cooled system that you would probably put into in a computer, right? I'm already literally running coolant into the engine block directly adjacent to the source of heat.
yes, but heat pipes have a lot of capacity actually get short from a relatively small point pass it out, and then you can do whatever bigger cooling system you might need. I
Yeah,
don't know if it's ever considered or if that's.
but a liquid cooling system will always beat a heat pipe system.
I think the problem too is if you think about it, CPU, when it runs super hot, it's still only putting out so much energy, right? It's just a little tiny thing. Your engine is this giant oven that is just, even if you heat pipe it away with a lot of efficiency, how are you
I guess the important part, what Rick said, is that having the cooling system, the water cooling system, as close to the engine block weakens the structure, right? And you can get a lot of joules per second on a relatively small heat pipe. This is why I'm suggesting heat pipes to get it, at least the initial thing away, and then you work on
When you get it away, how do you cool it so you can bring it back to cool again?
Well, so
then the regular water cooling, right? You just bigger
so think.
That's what I'm saying. We don't. It's too much heat. Like if you run the engine hot, that heat, like the hotter you run your engine, the more energy you generate. You have to cool it somewhere, even if you efficiently take it away.
But it's easy to add a bigger radiator, right? But it's not
But
so
not if the
easy.
radiator is the size of your car. Like if you make the engine twice as hot, it's a lot more energy.
So let me also put out there that drag race car has as large a radiator as you can fit in the front of the car. It has an electric water pump. Mechanical water pumps become problematic at extremely high RPMs, but you can get basically running, easily tens of gallons per minute, hundreds of gallons per minute of flow rate through these things. Like, you are already moving as much heat as you possibly can. Now keep in mind that the actual engine block designs, they used to be like cast iron, and they've gone to weight savings and also energy transfer. So nowadays you're going to have an aluminum engine block. You actually have fairly efficient energy transfer through the block. You would have to move to something like copper as the entire engine block to get better heat transfer there, but then you end up with a much weaker material. So the trade-off is in how you actually keep the strength of the material up as you get to extremely high temperatures and have really low thermal resistivity, but really high thermal transfer.
I have another question. So I have very old cars that have mechanically linked valves, so I always heard about electronic controlled valves. I thought, oh, they're completely decoupled from the engine. But what you're saying is even in the fancy new cars with electronic valves, they're really still mechanically linked to the cam and only have a certain degree that they can change their opening and closing. They're not completely random.
Yeah, when you have variable valve timing, it's sort of adjusting within a range. There's a whole variety of systems for it, but nobody has actually gotten, well, there's a couple of prototype engines out there that actually run effectively solenoids on the individual valves.
Production car, they're all still mechanically linked.
Yep. Yes?
Are the ECUs in your system networked anywhere, or are you running on all of them?
So in the Cobra, it's actually it's strange for a drag race car, but it actually has power steering. It has power door locks, power windows. The remote control still works. No, so the story on that is we actually bought the car built, and the previous owner lived in Pennsylvania where it was street legal. It was his daily driver. So all those systems are actually running the OEM modules, so like the chassis control modules and everything for the lighting and stuff like that. In the aftermarket ECU that we're using was actually made in the late 90s. It doesn't really talk to anything else. In a modern system, if you look at, say, Haltech or Link or any of the modern ECU vendors in the aftermarket space, they do have a whole bunch of interfaces for, here's your CAN interface. You'll link things like your wideband fuel controller will often be a separate module, and you'll use CAN to interface the two. You'll hook up to your instrument cluster that way. With an older system like this, the Cobra's dashboard is primarily analog, so it's actually just running PWM pulses to run the tach and stuff like that. Cool.